Okay. Well, today we're going to continue talking about multi-particle entanglement. But let me say that you really a great crowd yesterday. There were so many questions, and please go ahead, ask just as many questions as you had last. Here's one. Yeah. Very good. Yeah. Yes. Yeah. Oh, but well, we can just solve the exercise maybe. Should we start by doing that? And then we'll see what happens. I mean, if you write T tensor GZ or GZ tensor T, that's sort of like the same up to maybe a local basis change. So it depends a little bit how we write it down. Should we just do it? Does someone want to try to do it on the board? You can try. No? Anyone else? Okay, I'll have more exercises for you as we go along. Actually, I have made a long list of exercises. But we'll see. I'll try to not forget posing them to you. Okay, so the exercise was T tensor T is equal to T tensor JZ. And you were remarking that maybe these should be swapped. That was your point? Okay, yeah, that may be true. But it doesn't really matter so much. So let's just try to solve it. So what's the left-hand side? Right. So we start with T tensor T. And what does that mean? Well, it just means sum over Tijk EI tensor EJ tensor EK plus sum over Tijk EI. And now these guys we have to take the new basis, right, orthogonal vectors to this here. Right, so we have now the dimension, because it's this direct sum. When this guy here lived in dimension ABC, then this one here lives in dimension 2A, 2B, 2C. So we put a tilde up here. Oh, that must be a J here. Okay. Now, right. So we can think of these first vectors EI. So say, right, these are the vectors that have, all right, one. This is like E1 would be, if this was my original dimension A, E1 would be 1, 0, 0 up to here, and then I have another A zeros down here, and this would be, say, E1, and the E1 tilde, that would be this guy here. It's like zeros all the way up to here, and then it has 1, 0 up to here. Okay, so this is the way I'm kind of embedding it into this direct sum. And now you can notice that what I could do is I could write E1 as say E1 hat, where this is just this vector here. Right. So as E1 hat, so I can write E1 in this way. Let me wipe this. So that's actually the same as saying it's 1, 0, 0, where there's only A of them, tensor, say 1, 0, right? And I can write E1 tilde as, 1, all the zeros here, tensor 0, 1. And I could do it this way around, or I can do it the other way around. So I think it doesn't really matter so much. Maybe you want it the other way around, because then it conforms to this, I guess, better. Okay. Oh. If you want, you can swap them here. So, and then what you see is, all right, and what you see is that T direct sum T is actually equal to sum over Ti jk, And then I have EI tensor EJ tensor EK, where I now, let me call it hat. Let me call these guys hat, these guys here. Just not to confuse ourselves, I'm making a new basis. All right. And then tensor, and these small ones here, let me call this F2 and this here F1. Then what I see here is that I have either, right, I have them from the first term, and this is like F1 tensor, F1 tensor, F1, or I have them from the second term, which then would be F2 tensor, F2 tensor, F2. And this one is independent of the Tijk, so I just make a bracket, and then you see that's the same as ST tensor GHZ, or if you want to kind of change convention a little bit, you can swap them around. Okay, so it's a kind of like fairly straightforward manipulation with these definitions. I think it's nice to get used to the direct sum and the tensor product. And you see what maybe is a little bit confusing is that, right, this guy goes with this first term, and the second goes with this term, and the second, and the third one goes with this term. So it looks like it's really only a tensor of order 3 or a 3-particle state, because they're kind of like grouped in this way. All right. Yes? That's right. So I like very much to I like very much to change this one and give it a new symbol actually, and call it this with the box. I didn't want to introduce too much notation and too much complication. So yes. So if you want to be very clear, when you do the Kronecker and when you do the honest tensor product, then I recommend using this kind of little symbol. Okay. I can do so in the rest of the lecture if you want. Yeah. 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 Under the direct sum. All right. So under the direct sum, in this particular case here, right, we had the T was an element of CA tensor, CB tensor, CC, and then the T direct sum T is an element of CA direct sum CA tensor CB direct sum CB tensor CC direct sum CC. So but this is the same as C2A. Okay. Oh, if they didn't belong to the same dimensionality, then you just it adds up. It adds up on the direct sum. So dimension sums up on the direct sum, and it multiplies under tensor product. Sum goes with sum, product goes with product. I think that's probably maybe also where the name comes from. Okay. Well, all set. We talked about this notion of restriction. There's another question. Yes. 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 Well, I'll come. Yes, actually, a lot of you asked me afterwards about this connection to SLOCC that I mentioned, and I maybe just want to spend a couple of minutes explaining this to everyone again, because I only made it as a side remark. So we had this notion of restriction, right? So we had T. So T was, and actually, I'm not going to repeat this now. The T is, I have the T in ABC and the T prime in A prime, B prime, C prime, right? So I don't need to write it down the whole time. I'll say when it changes, we say T restricts to T prime. And we call this restriction if there exist linear maps A from CA to CA prime, B from CB to CB prime, and C from CC to CC prime, such that A tensor B tensor C applied on T is equal to T prime. Okay. So, right. So, important thing to notice here is that these T's are pure quantum states. Okay, nothing to do with density matrices. We just talk about pure quantum states. Good old quantum mechanics, like in every old textbook you open, there's no mention of mixed states. It will just start with like saying, psi is an element in some Hilbert space, right? And in our world, psi is called T, and the Hilbert space is some CD, right? And actually the CD has some substructure, namely it's a tensor product of some CA, tensor CB, tensor CC. Okay? So it's a very special case of this quantum mechanical thing. So normally in quantum mechanics you can only do unitary basically, right? And you can do measurement. And now imagine that I only allow you to do local unitaries and I only allow you to do local measurements. But then I'm also allowing you to post-select on a particular outcome. And in that case, it turns out that you can enact these kind of transformations, where A, B, and C are just some linear maps. And I mentioned this connection to SLOCC, so that's sort of like maybe the in-words motivation. But in quantum information, people say, instead of restriction, instead of saying T restricts to T prime, they would say T maybe slot converts, SLOCC converts, or it can be converted to T prime. And where does that come from? Okay, and it kind of like comes from what I just said, but let me make it more formal. So Fernando introduced this class of operations LOCC, and it was a very, very complicated class of transformations. And what was LOCC? LOCC was stuff that you could do. So if you have three particles, they're, one particle here, the CA particle here, the CB particle here, the particle over here. Then LOCC, where the things that you could do locally, right? You do some operation locally, then you send some classical information to the other party that does something locally, sends the classical information to the other party, does something locally, and an infinitely number of rounds possibly of doing this. Okay, that was LOCC, and this class of operations LOCC is kind of like defined as actions on mixed states. Okay, so mixed states, mixed quantum states, they're density operators on that space, right? So they themselves are matrices on that space. So rho is, in our case, if I now take the CD, is some matrix, right? So it's a just say it's a matrix of it's a D by D matrix, and if it's a density matrix, it's positive semi-definite, and maybe it has trace 1 as well. Okay, And then when people speak about LOCC, they write down this map. So they say lambda is a LOCC. And then lambda is some map, some quantum operation. So it's a quantum operation. Quantum operation, which means it's a CPTP map operation. Okay. It's a CPTP map, so completely positive and trace preserving. But you could also just think of it as a quantum operation. And then you can act with this on rho, right? Now, if lambda is an LOCC, the lambda actually has a very particular form. And this is not an if and only if, but lambda has the following form. It can be written in the following form. It can be written as AI tensor BI tensor CI applied on rho, and then AI dagger tensor BI dagger tensor CI dagger. Okay, where these are just arbitrary linear maps, you know, from 1 up to something, okay, up to some L. And this we call the form of such an operator, we call it separable. So it's a separable superoperator, some people would say, but any LOCC map has this form. And the I that you see here as an index is this, it can be taken to be the same for all of them and kind of corresponds to the classical communication or to the entire transcript of the classical outcomes obtained during your LOCC protocol, right? This super complicated thing. You do measurements, you record something, someone else does something, and so on. And this form, and now you could imagine the following, right? You could imagine that you are only interested, right? You know, so you could think of like the I is the classical information, and given the I, my post-measurement state is actually this. But now imagine you're just interested in this particular I. For instance, I equals 5, right? So you're only interested if your display comes up 5, then you're interested in it, and otherwise you don't care. So what are you going to do? You're going to start your experiment, you're going to run it, and if it doesn't come out 5, you just trash it and you run it again from scratch until your display shows 5. If the probability of this I equals 5 showing up was non-zero, then at some point this will happen. So, and if we don't care how often we run it, then actually we could say, well, I can actually do a transformation that brings me from rho to just this one particular term. But since we don't care about how often we have to run it, it's not kind of like a deterministic operation. It's not like I have to run it many times maybe to get there. So that's why people call it a stochastic operation. So if I kind of like press the button until I get it right, I call it a stochastic operation. But so basically what we could do is we could start from rho and we could make a rho prime out of it, and we could say, well, okay, so this, and we chose some I, okay, I call it I0. And you know, if we don't care how often we run it, this here is our operation. Right? And actually, if we don't care how often we run it, then also we don't really care about the normalization of this thing anyway. Okay, so then under, if we are happy to add to you know, this S for stochastic, okay, then actually we can make a bigger class of operations. We can just go to each thing here. We can pick one, and we can go here. And now, we, in this course, in this class, are only interested in pure states, right? Because they're kind of nicer and easier and more pure and so on. So we're only interested in pure states. So we're only interested in, and in our notation, in the normal quantum mechanical notation, we would say we're interested in these pure states, right? But I'm kind of like, I was avoiding this bracket notation. So in my notation, it would be it would be TT star, okay, or TT dagger. It's the same thing, really, right? This is just the normal my tensor, and this here is just the dual, right? Okay, so, and if I now plug this in, then what do I get? Then, you know, then T gives AI0 tensor BI0 tensor CI0 applied on T. All right. On the other side, we just get the Hermitian conjugate of that. Okay. It's just because, oh, I forgot the daggers here. You have to tell me if I make mistakes like this. All right. All right. The dagger and the star are the same. Dagger equals star. So you can put a dagger or a star, whatever you like. Okay. Yes, I guess it's larger some way. But we don't care about the probability. So yes, I mean here you have a normalization condition. That's a difficult question. Graham, do you know the immediate answer? It's kind of bigger. It depends how I now. In my A, I can put. Yes. Okay, but so like if I don't care, if I only care about the, if I only care, if I don't care about the probability of the output, then it's a bigger set. Yeah. Yes. So I'm only going to, so yes. All right. So what do I want to say? Well, what you see here is that what happens with these operations with SLOCC is that my quantum state gets transformed, right? My T just gets transformed by some linear maps, A, B, C. Right? The I0 was some fixed I0, so I can just drop it. So SLOCC really means taking T and applying some linear maps on it. And you see now where the linear maps come from. They come from the Krauss operator description of this LOCC map. Okay, so they're like Krauss operators. Yes. Yes, they're completely positive, right? You can make a completely positive map out of it. That's not trace preserving. Yes, that's right. It's not trace preserving, but I only keep one term. Or if I normalize the length of it, or what do you mean? Yes, I'm not doing that. Yes. Yeah, it's bigger. No, because you can even do it locally. So I find the name also quite. You can do it locally. You can just make a unitary followed by a projection, and this way you can get any A. And so you can actually do it locally. So but plus that you post select. So it's not a restriction. It's actually an if and only if. Sorry. Yes, we keep only one term. But as one of, I think you mentioned before, is if we want a pure outcome, a pure set as a result, which we are interested in, then this is without loss of generality, because if it was a sum of two terms, then and the terms would be different, then it would not be a pure state anymore. So from that point of view, if we restrict to pure states, this is the right class of operations to look at. No, I have not introduced the equality sign for tensors. Okay, we will not use we will not really use an equality sign for tensors. Only if it's the actual same tensor. I'll come to that. Let me just repeat it. Let me introduce some notation for that, so we don't get confused at that point. Okay, well, that sort of hope that sort of like explains a little bit of the interplay of LOCC and SLOCC. There's another question. Go ahead. Yes. Right, but this is sort of like, I mean, every LOCC map has this, it's a subset of the separable superoperators, and separable superoperators have this form. So any LOCC map can be written in this form. Yeah, I don't know exactly what Fernando wrote down, but oh, it doesn't have the classical. You can tensor an I here if you want. Did he do that? Maybe we take it later. Okay. Yes. Okay. So there was a very good question with respect to this restriction notation. Okay. So we will, if t is bigger than t prime, and if t prime is bigger than t, then we will actually we will give it a sign, and we'll say t is equivalent to t prime. Okay. We'll not use equality sign for that case. Equality sign will only use if the tensors are actually equal. All right. One way of having this this equivalence here is by having the transformations from here to here being done by invertible operations. Right? So like an example. Right? Example, if ABC invertible and implementing t bigger t prime, then of course I can just, then of course A inverse, B inverse, C inverse implement t prime bigger than t, right? And of course, in this case, t, well, in this case, of course, t is equivalent to t prime. Right? But there are other ways of having an equivalence here. So these ones here, where they're invertible, actually they're a special case, and sometimes I like to, I'd like to call this, if this happens, right? If they're invertible implementing it, then I'd like to say that t is isomorphic to t prime. In some sense, right, then really nothing happens, right? If I transform them by invertible operations, then it's really just like a basis pane. Yes, so just take the tensor T, take some tensor T, you put it in, it's in ABC, and then you actually kind of like take the same tensor and you embed it in some higher dimension. So you put it, you take the same tensor. Maybe I just write it in this other notation now that you have learned it before. I tensor it with a zero tensor, okay? Well, just this complete zero matrix in some in some dimensional space. Then of course that's the same, right? So then this guy here lives in some dimension that's a little higher, right? It will live in like CA direct sum, maybe CA prime, where this is like living in CA prime, etc. And obviously T and T, this is my T prime. Obviously T and T prime cannot be connected via an invertible transformation because from A to this space here, there is no invertible transformation. They're all, because they're rectangular. They're not square. These dimensions are different. So it's kind of like for trivial reason, this one and this one here, they're not isomorphic. Okay? So T is not isomorphic to T prime for the trivial reason that they're no square matrices. But of course, there are linear matrices that bring me from here to here. Namely the matrix, that's the identity matrix, and then zeros in the rest, right? And from here to here as well, right? So just the identity matrix, and it projects away the other stuff, right? So, of course, they are isomorphic, but they're not equivalent. And yeah, it's kind of the only example. I'm afraid. I think so. Oh well. Can we do? But yeah, sorry, I didn't want to dwell too much because it is kind of trivial. But anyway, someone asked, what can you do? So we'll well, let's look at some examples. Okay, so some more non-trivial examples. Right. So now you know basically if you apply some local GLs, then you know it's not so interesting. I mean, we should. Okay, so I have three types of examples, three classes of examples for you. And example one is, of course, our familiar example where the what I call the matrix, right, where the dimension of the last space is 1. Okay, we got to start easy, right? So then T, because you know I can do these local invertible transformations on it now basically for free. So in particular, I can I can bring it into the Schmidt decomposition form. Right? You saw the Schmidt decomposition. I think Fernando did the Schmidt decomposition. Right? So for free, I can apply these local unitaries. They will bring me to some isomorphic tensor in Schmidt decomposition. Okay? So T, I started off with some T, but of course T will be even isomorphic. Okay, so let's try to use this very precisely to its Schmidt decomposition form. And what's the Schmidt decomposition form? Well, I mean, I chose some basis. Now I just decided to choose my basis such that it's in this form. And these here are the so-called Schmidt decompositions, Schmidt coefficients. These are the Schmidt coefficients. And now I chose my basis so that it's the Schmidt basis. Now, how do I, but now I can actually do more. And what is this? This here goes from 1 to R, where R is the so-called Schmidt rank of the state. But notice that d sigma I here, I chose the R, okay? It's like the R, so all of these numbers here are non-zero. Because I just only sum up to the Schmidt rank of the state. Now what I can do is I can make a matrix A which just is which just looks like that. Right? It has like the first eigenvalue, the first, and they're not only non-zero, they're also positive. They're actually strictly positive values because they're the Schmidt coefficients. So I just put them in a matrix. Okay, I make the matrix a little bigger, so it's better to see. It's a diagonal matrix, and it has zeros here, and here it goes up to the Schmidt rank. Okay, and then up here I just put zeros as well. Okay, that's a nice linear map, and if I apply this map on, say, the first vector space, what it does is like rescales these EIs, right? And it will eliminate the sigma i's. So you see that this is actually equivalent to I from 1 to R of EI tensor EI. And this one you know. This is just what I call the EPR state of rank R. Okay. Okay. So we can bring under this class of operations, we're allowed to do very powerful things, right? I give you some non-maximally entangled state with some Schmidt coefficients, and I can just make them all equal and make it maximally entangled. Question? Sorry? Why they're at the block of zeros? Because my Schmidt rank might be lower than my local dimension. So if my local dimension was A, then here I have A minus R rows, and then here is like R rows. But you're right, it's kind of like, doesn't feel that important, right? I like to wipe these things under the carpet often. I'm just trying to make it a little precise here, but yes, it's not so much. Okay, very good. So now that we know that every T, basically they're only EPR states of rank R. Okay, so in a given dimension, CA, CB, C, under this SLOCC operations, I have these different sizes R. Yes. You can. Maybe we come to that later. We'll come to that later. It's, of course, you're given a class of operations, and then you can ask yourself, what can I distill from it? You know, like Fernando had LOCC and asked, well, how much can I distill? We are having SLOCC, and we can also ask, how much can we distill? But we'll do that a little later today. For the moment, we're just trying to understand which states restrict to each other, which tensors restrict to each other, and which don't. Yes? Yeah, we're just doing an example. Okay, so let's continue with this example, because I now know that every state is equivalent to some EPR state of some Schmidt rank R, right? That it's Schmidt rank. So now what do? I have to now understand when does the Schmidt rank R state restrict to some, when does, right? So how, when is EPR R related to EPR R prime, right? I give you now two different guys of these. When can I restrict from R to R prime? What's your guess? R prime less than R, right? So this is true for R prime less than R. And how do we see that? Right? What's the restriction if R prime is less than R? What's the map that implements this? Yes, it's so identity with some zeros, right? So I'm maybe, and it's sufficient actually to do it on one party. The other parties can just do identity, just like here, or I mean the other party, because I have only two. So what is my map? My map is just the identity map. So it's 1, 1, 1 up to R prime. Okay, and the rest 0. So I just basically, and the map has still dimension A, right? So this is like A minus R prime. So what will that do? It will take my it will just take these EIs here, and it will send them to 0 when their index is higher than R prime. Okay? So what does this A do? The A takes EI, and it sends it to EI if I is smaller than R prime, and the map takes EI, and it sends it to and it sends it to 0 if I is bigger than R prime. Okay? It's one example of a map. You can do other maps also that do the job. Yes? Yeah. Absolutely. Yeah. Yes. But as you say, the probability kind of like goes inverse with that, right? Okay, but it's sort of like you see that life kind of gets easier with this slog stuff, right? Because there are not that many states around, and I can convert stuff to EPR pairs that wasn't EPR pairs before. So things get a little easier. But notice that you can't, right? We just implemented this going from R to R prime, but you can't go up. So the Schmidt rank can only go down. I'll leave it as an exercise. Convince yourself that you can't go up. You can only go down. So it does still tell us something, right? The Schmidt rank is the Schmidt rank gives you the information about the entanglement, but it's a little bit of information, but it's very useful to know that your Schmidt rank can't go up. Okay. All right. So what's the next thing? So, right, Schmidt rank tells you the answer here. We have another example for you. You know, it's the same. We're running with the same examples the whole time. The next example is A equals B equals C equals 2. Okay. 3-qubit states. We have already seen a bunch of them, and now we want to bring kind of like order into them. I'm not going to give you full proof of all of this, but I want to tell you the story. So they're basically 6 different types of states up to isomorphism. Okay, there are 6. So up here, right? Up here we show that up to isomorphism we had R, this parameter, the Schmidt rank parameter, right? And that was going from, you know, the Schmidt rank was 1, 2, 3, 4, 5 up to A, which was kind of like, say, the minimal dimension of A and B. Here in the 2x2x2 case, we have 6 different types or types of tensors up to isomorphism, right? Which was this notion there. Oh no, it's underlined it. That was of course misleading. Up to isomorphism, okay? And what are those? You can guess, of course. I'm just telling you. They are the GHZ state. There is this W state. And then these are just 2, right? But there's we also know that we can of course take an EPR state on, say, Alice and Bob and tensor it with a product state on Charlie. All right, so I can do an EPR on Alice and Bob, tensor some say E1, and I can write this out. Right? Actually, it will be convenient to write them all out. Well, let me do it like this first. And this is like on C. And EPR BC. No, that was in the middle. EPR AC tensor the E1 on B. And here I have the EPR on BC tensor the E1 on A. And then down here we have a product state. Okay? So these are actually the 6 classes that one has. Right. So these are 6 classes up to isomorphism. Vidal and Chirac did this, and probably this kind of like stuff in the tensor literature that was known in the 19th century. But in our language, we now want to understand, just as we had tried to understand how these are related for different R and R prime, we now want to understand how these 6 classes are related. Right? Can you restrict? What can you restrict to what? And for that, let's just maybe start. Let's just look at them and let's understand their relations and understand how we can implement the relations. You know, it's interesting from a mathematical point of view, but if you're an experimentalist, you actually might want to do it in a lab, and so it's good to know how to do it. Especially since 3 qubits is already kind of like a challenge for many architectures. Okay, so here we go. Let's start with this relation. So I already brought them in order, but let's start with how can I convert this EPR state to this one here, right? So I claim that I can restrict from this to this. Okay, so maybe let me write down what the first one is. It's E1, E1, E1 plus E2, E2, E2. Right. Tensor E1. How do I restrict to E1, E1, E1? Who knows the map? Yes, so the map here, the map A would be 1, 0, 0, 0. That's what you want to apply, right? It's exactly, that's right. It's exactly this. It's also no surprise that it's exactly such an implementation like this, because it's because the third factor really doesn't play any role here. Okay, all we need to do is we need to kill the E2. So our linear map just sends E2 to 0, and it leaves E1 untouched. And with this map, you implement this relation, and E1 tensor E1 tensor E1. You end up with this, right? Is this clear to everyone? Do ask if it's not clear. Yes. You mean my B and C are identity? Yes. Yeah, I need to always give you 3 maps. That's very good. And B and C, they do nothing. But as a matter of fact, they could also do this map and it wouldn't do anything. It would do the same thing. Okay, there's often many ways of implementing restriction. When did we start? Like, how much time do I have? I forgot the time. Is it till 12 or till 12:30? 12:30. Great. Sorry. Okay. Okay. So we understand this one, right? Okay. Let's do. Right. And by symmetry, you also understand why this happens, right? And why this happens. Okay. Very good. So now let's understand how we go from GHZ to this one here. Okay. So we start with the GHZ, which is E1 tensor E1 tensor E1 plus E2 tensor E2 tensor E2, and we want to go to our EPR pair, right? Which is like this one. So what's the map that does that job? What's the triple of maps job? Yes. So I choose for A equal B, I do nothing, right? And on the last one, I choose 1, 1, 0, 0. Okay. And so in other words, what it does it maps the E1, right? The map maps the E1 to E1, and it maps E2 also to E1. Okay, this is an example of a non-invertible map. Actually, these were also examples of non-invertible maps, but maybe less interesting ones. They will do this job. Okay. Very good. Okay, so now we understand this. Let's see, and by symmetry, of course, it gives you also these other relations, right? So we can just like fill the picture in. All right, also this one. Well, I just put an arrow, right? You know what it means. Okay, so we are kind of left with understanding what happens with the W state. So it's good we practice on the easy examples. So we can do the W. It's a little more complicated. But just a little more. Okay, so we want to understand the W. That was E1, E1, E2, plus E1, E2, E1, plus, I'm sorry, I'm not using this bracket notation, but I don't want to change it now. Life would be easier, it's true. But I want to go to E1, E1, plus E2, E2, tensor E1. Okay? So how to do this? Any idea? Yes. Okay, what do I do on 0? Just tell me, so what's the... Okay, so on C, you're saying what I do is I project out, I project away the 2, right? Exactly, we just kick this out. Dang. And then I have E1, and then I have E1, 2 plus E2, 1. Right? So what do I do now? It's not exactly in that form yet. Okay, some other people helping. Go ahead. Identity on A, and we don't really call it swap. 0, 1, 1, 0, what's it called? X. It's called X. People sometimes call it X. That's probably X operator. Bit flip, right? It's a bit flip operator. Right? It flips a bit from 2 to 1, and then yeah, my bits are 1 and 2. All right, so it flips the 2 and the 1 around, and then I'm home. Okay, very good. So by symmetry, of course, all these other also have here. Okay, so you know I have this one, and then I have the other ones, and so on. So the big question is, what happens here? What happens here? And I leave it as an exercise to show that they are not comparable. Okay, neither restricts to the other, and so W does not restrict to GHZ, and GHZ does not restrict to W. Exercise. See, in the lecture we only do the easy things. Should I give you a hint? Okay. So maybe you can give the hint. Why does the GHZ not restrict to the W? So look at the W and look at the GHZ. Okay, just very naively. Right? W, GHZ, you look at them. Why can you not get a W from the GHZ? Yes, it has kind of like, the W seems to have 3 terms, right? The GHZ has only 2 terms. But somehow term creation is not really part of this thing. Well, it's sort of like, okay, so one can make this precise. So the W has rank 3 in some sense. We'll define later what rank is. And the other one has rank 2. So later on, we'll introduce some tools to make this happen. The W also doesn't restrict to GHZ. Why does the W not restrict to the GZ? Now you can't argue with the number of terms because it has more. That's right, yes. That's right. It wasn't like a full argument. Graham just asked for the intuition. Okay? All right. Yes. All right. Yeah. They're not comparable either. Yes. They're not comparable either. Yes. Think a little bit about it, maybe. Let's just move on. Yeah. Otherwise, we're not. Okay. Good. I want to give you another example. Graham has actually been asking for this example just before. You want to make sure that that the surprise arrives. Let's see if I can surprise you. But you know what the last example is going to be, right? It's going to be the Mamu. All right. What else? All right. All right, it's 3 EPR pairs in a circle. All right, Mamu 2, dimension 2, 3 EPR pairs in a circle. It's like C4, 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 that's the dimensions. Okay, so I want to know, you're given a GZ state with R levels, and you want to create this thing. Okay, what does your R have to be? Can you give some, how many terms, what do you think this R has to be? Oh, the objective is to find, to give a valid R, to find an R, so a GZ with like R levels, such that this restriction is true. Three is not correct. 64 is correct, but it's a bit large. Maybe we can do better. 8, there was 8. Why 8? Yes. Right. So if I can get an EPR pair, right? I can get an EPR pair and even an EPR pair tensor something from a GZ level 2, right? And now I have 3 EPR pairs in a circle here. So I just take 3 GZ states and I create it. So I have these, like, the first one I need a GZ, the second one I need a GZ, this one also. But these are 3 EPR pairs tensor together. So I need 3 GZ states. If I take 3 GZ states tensor together, they will do this. So the one correct answer is this tensor 3, right? Which is the same as, which is really the same as GHZ of 2 to the 3, and 2 to the 3 was 8, all right? Okay, this is correct. Can you do better? And that was 8. Okay. You can think about what is the lower bound. What's the lower bound? Can I do it with 3? I said there was someone that said, can I do it with 3? I said no. 4, yeah. So, well, okay. So, how do I do a lower bound? Okay, so let me tell you how to do a lower bound. I'm giving you a graphical lower bound. I hope it satisfies you. So, this notion of restriction is monotone under grouping particles together. Okay? So if I have something, and let me do this grouping. Let me do this graphically in this example. So if I have a restriction, I just repeat the picture because I don't want to destroy that. If I have some restriction here with some number r that enacts this, then I can group the particles together. Say I group, right? These are three particles. Right? Here's one, and here's one. Say I group those two together. Okay. Then what happens? Kind of running out of space. Then what happens is I'm doing it in red. So I'm grouping these two together. Okay. Okay. Then you see that there are two EPR pairs between these two particles, this big one and this one. And on this side, what happens when I take a GHZ state and I group two of the particles is actually then I end up with an EPR state of that same rank. Okay. But now, after grouping, I have an EPR state here, tensor product of two PRs, so that's an EPR of level 4. Right? And so, by our discussion on the blackboard on the other side, the R here can't be lower than 4. Okay? So from this kind of argument, it's called a flattening argument, because it's like taking a tensor and flatten it. It's like the mathematical command is called flatten. So you flatten your tensor, your array to a matrix. Then from this we know now, from this argument, we see that R has to be bigger than 4. Okay, so we got some room to play. So flattening argument gives you a lower bound of 4, gives you an upper bound of, we have an upper bound of 8, and we still don't know what the answer is. Okay, so there was so that was the state of the art in 1969, and then a person came along, Volker Strassen, who revolutionized the study of matrix multiplication by showing an upper bound of 7. And so he gave an upper bound of 7. He showed you can do it 7. Actually, 7 is the correct answer, so you can show that it's exactly equal to 7, but it's difficult to show it's equal to 7. So both the upper bound and the lower bound are actually difficult results. But I don't want to spare you this beautiful insight. So he showed, so Strassen, 1969, he showed that, of course, he used a different language. He didn't know what Greenberger, Horn, Teilinger. They only came up later. He showed that this is bigger than Mamu. Okay. And here's the decomposition. The first thing we should notice, is that when we have such a restriction, it gives us a way of writing this Mamu in 7 terms. So, and why is that? All right, so if I can write this here, if I can write this in 7 terms, and let me call these product terms alpha, beta, gamma, I, then, so if it's possible to write it in this way, then of course I can also degenerate from a GHZ state, because my maps then, the maps A is just the map that maps EI to alpha I, and the maps on B are the maps that map EI to beta I, and the maps on C, they're just the maps that send EI to gamma I, all right? And if you have such maps, then you can write it in this form. So an equivalent way of saying the GHZ level 7 restricts to Mamu 2 is to say Mamu can be written as a sum of 7 products. Okay, but now we have to do it, right? Yes. Yes. Sorry. Say again. Yes. That's correct. Yes. Oh, I mean that no. If okay, so let me write it down in a. I'll write it down in a. Yes, I'll try to answer. Hold on. Yeah, I'm sorry for this kind of like slang. Um, so I'm interested in understanding for which R this is possible. Right? Okay, so for which R is this statement true? Okay, that's the question that I'm having. For which R is the statement true? And then now there's a little observation, all right? Observation that if true for R0, then true for R bigger than R0. Okay, that's one observation. So so I call every specific R for which I show this is true, I call it an upper bound on the optimal R. Right? So there will be some optimal R, some minimal R, for which this statement is true. No, the minimal R. So next observation. The observation was that the minimal R. Okay, the minimal R is bigger than 4. That was so the minimal R is bigger than 4. And with that, all R for which this is possible have to be bigger than 4. Okay? But we still don't know. So the minimal, so we have now two bounds on the optimal R. Right? The optimal R is smaller than 8, smaller or equal to 8, and it's bigger or equal to 4. Question is, what is the optimal R? Is it 4, 5, 6, 7, or 8? And the answer turns out to be 7. And I'm not going to tell you why it can be smaller than why it cannot be smaller than 7, but I want to show you why it can be 7. Right? So the writing down, right? So writing down the Mamu state in 7 terms, right? So if you write it down in your normal expansion, just by definition, it looks like it has 8 terms. All right? You see that? I kind of like formulated it differently, but right? It's like an EPR, tensor, EPR, tensor, EPR. If you expand this, it's like 8 terms. So how do I get 7? I'm telling you now. So, and actually, the way to do it is actually just to write down one of the terms. This is kind of like the we don't need that anymore, so I'll just get rid of it. So actually, it's possible to remember this decomposition. So that's okay. We'll see that I have to look up anyway, so I can't remember it anyway. But I think it's you don't have to store in your 3 times 21 of these alphas, betas and gammas. So here's how you do it. So I claim, and I cannot verify the claim for you because it will take too long. The claim is that this is, I have to introduce some new notation, but you know them already. The plus and minus states, I'm sure you've seen. It's like E1 plus or minus E2, right? Or if you like the Racket notation, it's, okay? And we don't care about normalization, right? So we need those guys. So Christandl made use of this Hadamard transform already. And we start with E minus tensor E2. That's the first term, right? I have to produce 7 terms. I claim that's the first term. Then you look at the MAMU and you say, oh wow. Why do I write it like this, right? So I have, it's a locally on every side it's 2 qubits, right? So I'm just giving you the 2 qubits. So now the MAMU is cyclically symmetric. See that, right? So I can just, so why not take this and just shift it cyclically? I hope I didn't make a mistake here, but otherwise you'll be mad at me. I'll give you reference where it's correct for sure. But okay, shift once more cyclically. Did I do it correctly now? Shift, yeah. So we shift once more. So the E2 tensor E plus comes out. And then I have the E1 tensor E1. And then E minus tensor E2. Okay, great. So what other operations do we have? So we look at it. We look at MAMU again, and we notice that the EPR pair is invariant under simultaneous bit flip. Right? If I do bit flip on A and on B simultaneously, then it will still be the EPR pair. So it's another symmetry of this tensor. It's this bit flip. So why not take these 3 terms and then bit flip them all? Right? What happens when I bit flip all of them? The E minus turns into minus E minus. The E2, yeah, okay, maybe I should have, well, I'll write it 1, 2. The E2 turns into E1. The E2 turns into E1. The E plus stays E plus and doesn't get a phase. The E1 goes to E2. Okay, now and again like plus cyclic, right? Plus these 2 terms. So it's just you take these 3 terms and you just bit flip them and you get 3 terms. So I get 6 terms. And then the surprising thing is then you have to add a local EPR pair also. EPR tensor, EPR, tensor, EPR. Okay, well it's 2 qubits, right? So why not take an EPR state there? The EPR state has also the right symmetry. So that's it. These are 7 terms. Now you can do the lunch break and try to verify it. And in case I made a mistake, I write down an archive number where you see a correct way of doing it. But I think this is the right one. So if you look at this archive number, we write it in this kind of language in the beginning somewhere in the intro. You can just look at the intro here, and maybe just. Okay, so that's the MAMU. You can write it in 7 terms. Here it is. Quite amazing. I'll tell you later why this result was really important in 1969 and not just kind of like a little game by Volker Strassen, but why this. I will tell you later why it made them world famous in no time. He might have been famous already at the time, but I don't know that. But he hasn't been, and this for sure did it. So. Yeah, I'll maybe mention it later more. Oh no, this is this is this is for 2 by 2 matrix multiplication. Yes, 2 by 2. Yeah. But I'll tell you later how it's related to matrix multiplication. I need a few more ingredients in order to tell you why he got famous by that, right? For the moment, it's just a little game that I think is a bit astonishing that that 3 EPR pairs can actually be obtained from a GZ state of level 7. All right. So, but you know that there was something. I had an open question for you, or I kind of like told you that the JZ and the W are incomparable, and I kind of want to tell you now. Well, they're still incomparable and with restriction, but actually, in some sense, one can compare them, just not with restriction. So I want to tell you a little bit more about W and GZ. I think it's extremely illuminating. And one of the things that you might have noticed by now is that this notion of restriction, it's sort of like it's very hard to come by it's very hard to come by these maps here. It's very hard to decide when something is restricts to something else or not. And it turns out to be really hard to decide. I mean, it's in a computer science sense, it's an NP-hard problem, and especially this number that we computed here. Let me introduce this to you formally. It's the rank of a tensor. Right? We kind of like already noticed that the rank of a tensor here. Let me define it as the minimum R, such that the GZ state of level R degenerates to our tensor. And one statement of before was that the rank of the Mamu2 is actually equal to 7. And you know, what we did was we showed the smaller equal sign. Then there's other exercises one could do here. The rank of the W state, we discussed that before, is equal to 3. Someone mentioned, and so on. So one can play with this rank, and this rank here, you see, for you, the GZ state is kind of like your currency, right? Then this is like an SLOCC analogon to what Fernando has called the entanglement cost. Right? The entanglement cost was kind of like how many entangled states did I need to create my state, and that's the same here. How many levels of GZ state do I need to create the T? So in a quantum information language, this R of T, or maybe I write it more precisely. So in quantum information language, what we would say is we would say that the log, okay, it's now a long sentence. The log R of T is it's a single copy. I put it in brackets because I don't want to go too much into it right now. It's a single copy slog entanglement cost. All right, Fernando introduced entanglement cost. So Fernando introduced the entanglement cost. If you consider kind of like the same notion, you consider a single copy, you do slog instead of LOCC, and then the entanglement cost is the log of the rank, right? So we count the GZ levels here, but somehow if I want to convert it back into qubits, right, then I would want to count the log of it. The single copy is because here it just says T, and here it just says T. And later tomorrow, we'll also talk about the case when I look at like many copies of the T, right? Creating many copies of the T. And in quantum information language, you know, that's the usual, or in information theory, that's often the case, kind of like a Shannon type limit that people define. All right, so still have a few minutes, so let me tell you this story about the GZ. Yeah, so long story short, this thing here is NP hard to compute. Hostad proved this is NP hard, so it's a difficult business. And when you have difficult business, you try to simplify your life and maybe come up with some notions and ideas that make it easier to understand this R, which is called rank. Rank of a state. And we have already seen it a little bit, but it's not too hard to convince yourself that this R of T here is if you plug in if the dimension of the C system is 1 and T then is a matrix, then actually this is the same as matrix rank. Yes. seems contradictory to what? No. It's just 2, yeah. Sorry. When I don't put an index, I basically always mean 2. And before we talked about this, how many terms does the W state have, right? And somehow saying that R of W is 3, that's sort of like the formal way of saying it has 3 terms. Because someone said, oh, it looks like it has 3 terms. And what you have to do is you actually have to prove that it's 3, and then you know that you can't do with less than 3 terms in your decomposition. But we're not doing this right now. It's not too hard to do. Maybe if someone is interested, you can try a little bit out. All right, but we want to simplify our problem. And the way to simplify is actually to not ask for this restriction exactly, but to ask for it approximately. First, seems maybe to make the problem more difficult, but we'll introduce another symbol for that. So we'll say that T degenerates to T prime. So T degenerates to T prime if I can approximate this T prime arbitrarily well. So if there exist tensors Ti such that these Ti, such that T restricts to the Ti, okay? So T restricts to them, and the Ti approximate the T arbitrarily well. I goes to infinity. I goes to infinity. So there exists some tensors Ti where this index I is a natural number, and T has to restrict to Ti for all I, and if I take the limit of Ti, then I get T. Oh, T prime. Sorry. Yes. Sorry. Okay. Yes, you take the limit. You can take the limit entry-wise. Yes. You do the limit for every. So the T is like some cube, right? And you take every entry and you take the limit. Okay. So you can find some sequences of tensors such that that all have some sequence of tensors such that T restricts to them, and you approximate the T prime. Okay, very abstract definition. You think it's no. You're not happy with the limit here because it might not be well defined. Yes. Okay. So, but I'm just saying that there exists a set of Ti such that this is true and such that the limit is well defined and equals T prime. Okay. Yes. Sorry. We're just using the normal Euclidean distance. Okay, you can just it's like it's all the numbers are complex numbers, right? You just think of this like tensor as a cube. You take one specific number, and you just look at does that number converge, in the normal Euclidean distance, normal absolute value distance to that number. Okay. But you can also say this as a L2 distance goes to this or some other distance. It doesn't matter. We're in a finite dimensional space. It doesn't really matter what you do here. It's all going to be fine. Okay, but I think this is sort of a very hard to capture. So there's of course one thing that we should note immediately is that if T restricts right? If t restricts to t prime, then t also degenerates to t prime, right? Very important. Why? Well, I mean, of course there exist these ti's, namely I can take them all to be equal to t prime, right? And then of course t will restrict to t prime, and and the limit, I mean, it's just the same tensor all the way around, right? So this is sort of like it's good to know. It's kind of like a weaker version. The opposite will not be true. But I want to give you, I mean, I don't think this definition makes a lot of sense without having seen the following example. And the example has to be an example that involves all three factors. So my matrix business doesn't help me anymore because actually degeneration and restriction are the same in the matrix world. Okay, so maybe I should write this down. So if C is equal to 1, so if we're talking about matrices, then actually restriction, and now this is of course funny, is equal to degeneration. Okay, equals. Maybe I write equals. Equals degeneration. Okay? Okay, so, but here comes our funny, our good example. ABC equal 2, right? A equal B equals C equals 2. I want to show you now that the GHZ state degenerates to the W state. Okay? And we said before, without proof, but maybe you can, with this rank argument, you can maybe do it, is that it does not restrict to W. Okay? So let's do it. We got 3 minutes. All right. Here's how we do it. We start with the GHZ state, but because we want to write it down in this very, very slow notation. Okay. So this one restricts to the following tensor. Namely, what I do is I just take the E1, and I have to look on my cheat sheet. And what I'm going to do with E1, I'm going to map E1 to E1 plus epsilon. So I'm going to choose some epsilon. Okay, epsilon's positive. I'm going to divide 1 over epsilon, E1 plus E2, tensor 3. Okay, so all of these guys, they basically map it to E1 plus epsilon E2, and one of them maybe scales it with a 1 over epsilon factor. And then here, for this E2 thing, we just flip the sign. Okay, one of them flips the sign, say the first one. Okay. Oh, and it also gets this 1 over epsilon. No. Yeah, it also gets the 1 over epsilon term. Okay, is that okay, the restriction here? Basically, it has 2 terms, and I massage it into 2 other terms. All right, I map E1 to E1 plus epsilon E2, and I map E2 to E2, and then on one of the parties, I flip this. Then I stretch it all, with this 1 over epsilon, and then on one of the parties here, say I flip the sign of the E2 right before I do the map. Yeah, well, I need it now. Bear with me. Okay. And in a sense, I don't care, but you'll see why I wanted to have it here. Okay. Oh, there's a bracket missing. Okay. All right. So now, what do we do when we see something tensor 3? It's binomial expansion. Well, we'll just expand it. Right? You see, the first term in my expansion is E1 tensor. Oh, did I mess it up? Oh no, I wanted to have it. Sorry. Very good. Okay, I'm going to flip the 2 to 1. Okay, who cares? All right. So then we expand this here. We expand this here, and you see the first term showing up is E1 tensor E1 tensor E1. I mean, ignore that for a moment, right? E1 tensor E1 tensor E1. Well, that's just subtracted here. Okay? That term just goes away. So this is like 1 over epsilon. Put a big bracket, right? And then the E1 tensor E1 tensor E1 term goes away. The next term is E1 tensor E1 tensor epsilon E2, right? It's epsilon times E1 tensor E1 tensor E2, right? And now you see what happens already is that the other terms are just the permutations of this, right? Plus permutations of this, right? And then the next term is epsilon square times E1 tensor E2 tensor E2, okay? Plus, and then there's an epsilon cube term, right? But we don't care so much. So what happens now is on the next board. So, you know, I chose my 1 over epsilon carefully so it cancels with this one. And of course, this here is just my W state, right? 1 over epsilon with epsilon squared gives me a epsilon, you know, with some tensor behind it, right? Plus epsilon square, some tensor. Right? But these tensors here are fixed. So now you see that for all epsilon, right? For all epsilon, I have now a better and better approximation. So GHZ degenerates to. So this here is kind of my. These here are my TIs, right? If I choose, say, epsilon to be 1 over I, right? Then you see these are my TIs. So then I've produced some TIs such that GHZ restricts to this TI, and at the same time, the TIs for I going to infinity, of course, go to W. Right? That was just our definition of degeneration. Yes, that's right. Yeah. 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 Yes. I mean, it's impractical on sort of like an enhanced level, right? The restriction was also impractical because I didn't tell you what the probability was, right? If it was 10 to the minus 26, we were also just being happy before. And now we're being happy if we have a sequence such that it goes to 0. Not a big weakening from 10 to the minus 26. Right? It's true, it's a little weakening, right? We're happy if we can do it in the limit. So but for practical reasons, I mean, you might say, oh, I'm happy to approximate, you know, I'm choosing my epsilon now with some, you know, for some number, and I'm happy to approximate that state. And then I get this notion. So I think, you know, the probability goes down, but if you're happy with a certain probability, you know, you can fix your epsilon. I think it's fascinating. I think this is a really fascinating example somehow because I think everyone who's got 3 qubits in a lab should know about it, because you know, you can start with your GZ state and then you can produce your W state just approximately. You know, it would be nice to see this in a lab. Yes, yes, we can do that. We don't manage now anymore, but I will tell you how to do that tomorrow. How to show that the W doesn't degenerate to the GZ state. Oh, it's not an if and no, it's not an if and only if. So if T restricts to T prime, then RFT is bigger than RFT prime. That's true. All right. So T bigger than T prime implies RFT. That's a nice exercise. Oh, actually, I got some exercise for you. Hold on. Let me just think about what was a good one. Let me see if I wrote some down for you before. Yeah, there was certainly verify the Strassen thing. That was one. Let's see if I can find it. Yeah, verify Strassen's decomposition is one of them. Yes. So show. This is I have another good exercise for you. You remember this this grouping of the particles? So if you have 3 particles, that you can group them into 2. Right, so this is a really nice one. So this is exercise. So show that T is product if and only if when you group 2 of the particles together. So if T, when say you group particle B and C, and when T, A, B, C are both product. Okay. Right. If you take a tensor and you group 2 of the particles, you get a matrix. Right. This says that you have 2 ways of grouping it. If both ways result in a rank 1 matrix, then your tensor is actually product. There are 3 ways of grouping it. You can throw the third one in, but I think 2 are sufficient to do this exercise. So you can throw that in. And are all product. Okay. I'm kind of over time. If you have more questions, that's it. Yes, that's right. The reverse notion. That's called the subrank, and that's the analog of the distillable entanglement. Yeah, how many GZ states can I get out of my tensor? Right? That's another way. We're going to maybe talk a little bit more about that. But how many GZ states can I get out of it? Right? That's the analog, the distillable entanglement, and this is the entanglement cost. And you can play with these notions.